So in this lecture, we start the chapter number 8, Basic Electronics. Yeah, this is your last chapter in the syllabus. So what is the meaning of basic electronics, or what is the meaning of electronics? Have you any idea about this word, electronics? Can anyone explain me what is the meaning of electronics? Or what are the components we use in the electronic circuit? Is there any idea about this? Anyone have seen the electronic circuit? कोई electronic circuit જોઈ છે? Yes, please. Whatever you know, please give the answer. Yes, anyone? 25 number, Sushant. Sorry, Nishant. 25 number, Nishant. Hello. If you can hear my voice, બધાનો અવાજ આવે છે મારો? Hello.
Yes, sir.
બધા જાગો છો ને? સુતા નથી ને? All of you please say yes.
Yes, sir.
Yes, sir.
બધા જાગો છો.
Yes, sir.
Yes, sir.
ઠંડીમાં સૂઈ નથી ગયા ને બધા? જાગતા રહેજો, બરાબર છે? લાસ્ટ ચેપ્ટર જ છે આપણે હવે, બરાબર છે? કમ્પ્લીટ કરી દઈશું આપણે વિધિન અ વીક ઓર 2 week. ઓકે. So what is the electronics? Yes. Can anyone have an idea about this word? અથવા કોઈ electronic circuit જોઈ છે? What are the components in electronic circuit? Yes.
Capacitor, transistor, inductor.
Yes, very good, very good. Any other thing?
Circuit
બીજું શું
board.
આવે?
LED.
Electronic circuit.
LED.
Microchips.
Yes, chip. Okay, બરાબર છે. પછી
Circuit board.
Diodes.
diode. Okay, very good.
Thyristor. Thyristor.
થાઇરિસ્ટર. ઓકે, ભણી ગયા છો તમે? થાઇરિસ્ટર ભણી ગયા છો?
Sir, it calculate the amount of heat and
નહીં, તમે થાઇરિસ્ટર ભણી ગયા છો એકચ્યુઅલી?
No, sir.
મને
No,
ખ્યાલ નથી. ઓકે ઓકે, સરસ સરસ. બીજું કંઈ? બીજું શું આવે? What are the devices we use in electronic circuit as a switch? હમણાં બે ત્રણ તમે નામ તો આપ્યા છે. First is diode. Yes or no? Diode is what? One type of switch.
Yes, sir.
And which material is made up of? કયા મટીરિયલ માંથી બને છે diode?
Silicon and germanium.
It basically is silicon or germanium. Okay, so that material we call as a semiconductor material. Yes or no?
Yes, sir.
Okay, so all are the semiconductor devices we use in electronic circuit, like diode, transistor. Yeah. Another one say that the thyristor. Okay, thyristor is a very popular device to use as a switch. Yeah. But I think you know these two switch very well, diode and transistor. Clear? So in this chapter, we will discuss in more detail about this diode, its application, same way transistor, its application. Another switch like Zener diode, આપણે જોયું હતું practical માં. Zener diode as a voltage regulator. Okay, so that is also power electronic switch. So it is just like your mechanical switch. જેવું mechanical switch કામ કરે છે એવી જ રીતે electronic switch કામ કરે છે. Clear? To on and off your supply. When you connect the supply to the load, in between that this electronic switch is connected. Clear? If you on this switch, your supply is directly connected to the load side. If you open this switch, it will off. Clear? But here you open and close by the signal, electrical signal. Yeah, that's why it is called as the electrical switch or electronic switch. Yeah. So here we are, after that discussing this diode and transistor, we understand what is the application of this devices. Clear? So before going to discuss the detail about these devices, we understand that what is a semiconductor devices, or what is a semiconductor material from which all these devices are made up of. Clear? So semiconductor material, basically the germanium and silicon and carbon. These are the very popularly used devices, popularly used material to make this electronic switch. Generally, we use the germanium and silicon to make the diode. Okay. So this material has a property that they are neither a good conductor like a copper material nor an insulator like a glass or porcelain. Clear? Its characteristic is between conductor and insulator. એટલે બહુ conductor પણ ના કહેવાય અને insulator પણ ના કહેવાય. Clear? It means that characteristic is between these two materials, like conductor and insulator. So in other words, we can say that we already studied the resistivity in chapter first. That resistivity, this material, semiconductor material, that is lies between the conductor and insulator. Clear? So if resistivity is very high, it means this is a insulating material. If it is very low, so it is a conducting material. But if it is between this conductor and insulator, then it becomes that is a semiconductor material. Clear? So because of the semiconductor have some useful properties, these are extensively used in the electronic circuits, like for making a transistor and diode. Yeah. Before the invention of this transistor, we used the large bulky vacuum tube as a switch. Yeah. But after the invention of this transistor and diode, all the semiconductor devices we replaced by the switch, transistor and diode. So all the electronic circuit becomes very small. Now the transistor is a one top of family in the semiconductor devices. There are other also family like thyristor family. In that there are a number of semiconductor switch. Same like a diode. There are different types of diode in the power electronics. Okay, so that we use depend upon the different application. So there are so many devices, semiconductor devices become popular because of its advantage. So in this chapter we have focused our aspects on the different semiconductor devices. Okay, so first understand what is the property of this semiconductor material. So first is that resistivity of semiconductor is less than insulator, but it is more than conductor. Second is semiconductor have negative temperature coefficient of resistance. We already discussed what is the meaning of negative temperature coefficient. So is a negative temperature coefficient of meaning? याद करो, हमने discuss करेलू છે in one of the chapter. What is the meaning of negative temperature coefficient? Yes, anyone?
With increase in temperature, resistance will decrease.
Yes, very good. So as you increase the temperature of this material, its resistance will decreases. Clear? So that is called as a negative temperature coefficient of resistance. Like if you take the example of germanium, clear? At a very low temperature, but it is a good conductor, but at low temperature, it acts as an insulator. Clear? So as you increase the temperature, the resistance will decrease and it works as a conducting material. Third characteristic is that when a suitable metallic impurity is added into the semiconductor material, its current conducting property change appreciably. Clear? I think all of you know that in the P type or N type of semiconductor material, you add some impurities, clear, to enhance the characteristic or property of this material. So these impurities, like we added arsenic and gallium material, so that the conducting properties will enhance. It means resistivity of the material will decrease by adding this metallic impurity in the semiconductor material. So this property is the most important in the semiconductor devices. Because of that, we use semiconductor device in most of the power electronic circuit. So if you require the low resistive power electronic devices, so we add the more impurities into the semiconductor material, so we can get the enhanced conducting property in the material. Yeah, so these basically three are the most important properties of semiconductor material, and because of that it is popular and we generally use in all the semiconductor materials. Yeah. Now first we understand first semiconductor device is diode. Okay, I think all of you have know that what is a diode, its VI characteristics and its construction. Okay. Then also we understand that what is the actual application of this diode. Yeah. So All of you understand the diode construction and VI characteristic? બધાને ખ્યાલ છે? Or I repeat again? મારે repeat કરવાની જરૂર લાગે છે? All of you understand what is the construction, P type, N type, how current is flowing from P to N, why not from N to P? બધાને ખબર છે VI characteristics? You already learned in the practical also. Practical માં આપણે ભણી ગયા છો. ખ્યાલ છે બધાને?
Yes, sir.
Or I repeat again? Repeat કરવાની જરૂર છે?
Sir, once can you recall?
Okay. So diode is what? That is made up of two type of layer. One is P layer and another is N layer. Yeah. So if you want to operate this diode as a switch, yeah, so apply the positive voltage anode with respect to cathode. Yeah, then and then it will start conducting. But if you apply the positive voltage at cathode with respect to anode, what will happen? The depletion layer become very large, so it will not possible to break down this junction. So in the reverse bias condition, your diode is act as a open switch. Clear? Well, let's I recall it again by showing this one video so you can easily understand graphically. Let's first start the construction, basic construction, so you can understand it very well.
In this lecture, we will start a new chapter, semiconductor.
બધાને અવાજ આવે છે વિડિયોનો?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes.
Conductor diodes. This is the name of the chapter. And in this chapter, we will learn how a junction is formed between P-type and N-type semiconductor. We will also learn volt-ampere characteristics of the two-terminal device obtained by using PN junction. And the device is called as PN junction diode. So I will write this down. We will learn volt-ampere characteristics or VI characteristics of PN junction diode. PN junction diode is a two-terminal device, and there is a difference between PN junction and PN junction diode. We obtain PN junction diode by using the PN junction, and we can do this easily by attaching the metal contacts at the two terminals. So if I attach one metal contact like this, then we have PN junction diode by using the PN junction. We will do the same thing for this terminal also. And because of this, we have three possibilities. First possibility is no bias condition, no bias conditions. In second possibility, we have forward bias condition, and in third possibility, we have reverse bias condition. In this lecture, we will deal with no bias condition, and in the coming presentations, we will complete forward and reverse bias condition of the PN junction diode. Now there is one question. What is the meaning of bias? What do we mean by biasing the two-terminal device? So I will write this down. The meaning of bias. The term bias refers to the application of external voltage across the two terminals. When we apply external voltage across these two terminals, we call it biasing. I will write this down. Application of external voltage across the two terminals is called as bias. And if we apply no external voltage, it is called as no bias condition. So in this lecture, we are not going to apply any external voltage to this PN junction diode, and we will analyze the PN junction diode in this situation. The next thing is the BJT, the bipolar junction transistor. This chapter is very important because we will use the concepts and the theories developed in this chapter for learning BJT. BJT stands for bipolar junction transistor, and this is very important topic in analog electronics, and it depends on PN junction diode. So if you have better understanding of PN junction diode, you can easily understand the bipolar junction transistor. BJT is a 3-terminal device. This is 3-terminal device, and you can consider this as the device having two diodes. BJT you can consider as a device having two diodes in which one diode is biased by the current of other diode. So you can see how much it depends on the concept that we are going to learn. So without wasting any time, we will start with PN junction. We already know what is p-type and n-type semiconductor. In case of p-type semiconductor, we add trivalent impurities. In case of p-type semiconductor, we add trivalent impurities, and because of this we have holes as the majority charge carriers. On the other hand, for n-type semiconductor, we add pentavalent impurities, and because of this we have electrons as majority charge carriers. And if we talk about the minority charge carriers, then for p-type we have electrons as the minority charge carriers, and for n-type we have holes as minority charge carriers. And if you remember, the minority charge carriers depends only on temperature, because electron gains the thermal energy and breaks the covalent bond. So it only depends on the temperature, and it will not depend on the external voltage that we are applying. So this is something we already know, and now we have to see what will happen if we combine p-type and n-type semiconductor together. When we combine p-type and n-type semiconductors together by any means like diffusion or an implantation, these are the process to combine p and n-type semiconductors. We dope one side of the semiconductor with the trivalent impurities, and we dope other side of the semiconductor with pentavalent impurities. We will have p-type on one side like this, and we will have n-type on the other side. If we consider the p-type, I will clear this portion. If we consider the p-type, then we have positive immobile ions, or we can say acceptor ions. These are the acceptor ions, and we have holes as the majority charge carriers, and on n side we have donor ions, and electrons are the majority charge carriers. So this is what we have when we join p-type semiconductor and n-type semiconductor, and this is the junction. And if we talk about holes, then concentration of hole is higher on the p side as compared to the n side, and because of this we have concentration gradients of holes from p side to n side, and similarly we have concentration gradient of electrons from n side to p side. And if we try to understand this thing by the help of pressure difference, let's say we have A and B, these are the two regions, and pressure at A is PA and pressure at B is PB, and let's say PA is greater than PB, then air will flow from A to B, right? The same thing will happen with holes. On P side, concentration of hole is higher, so holes will move towards the N side like this. And if you talk about electrons, then concentration of electron is more on N side, so electrons will move to P side like this. And as you can see, we have movement of charge through the cross-sectional area. If we consider this junction, and let's say the area of junction is A, then there is movement of charge carriers through this area, and whenever this happens, there is current. And as this process, the process of movement of charge carriers from high concentration to low is called as diffusion, we call this current diffusion current. This process is called as diffusion, and the current is called as diffusion current. This diffusion current is very important, and we have to use it a lot while solving the numerical problems. And diffusion current is because of majority charge carriers. So we have one new thing with us, diffusion current. So let us try to understand it once more. Diffusion current is because of the movement of charge carriers, the majority charge carriers, from high concentration to low concentration. We call it diffusion current because the process of movement is called as diffusion, and this is because of majority charge carriers, right? The next important thing is depletion layer. Now we have to understand how depletion layer is formed in p-n junction diode. Because of diffusion, holes from p side combines with electron on n side, because we have electrons as the majority charge carriers on n side, and in the same way electrons from n side combine with the holes on p side, and as the recombination takes place, immobile ions will surface out. I will write this point down. Immobile ions will surface out because of what? Because of diffusion. Now what do we mean by immobile ions will surface out? What do we mean by surface out? Surface out is nothing but uncovering of immobile ions. This acceptor ions and this donor ions are immobile ions because they are fixed, they are not moving, and when we uncover them, we call immobile ions are surfaced out, because initially electrical neutrality was maintained. With acceptor ions we had holes, so electrical neutrality was maintained. In the same way with donor ions we had electrons, but as these holes are combining with electrons, we are left with positive and negative ions. Because of this, depletion layer is formed in p-n junction diode. The region with no mobile charges but only uncovered immobile ions is called as depletion region. I will write this down because this is important. Depletion region. In this region there is no mobile charges, but only uncovered immobile ions are there. And as I have already explained why there is no mobile charges, because the holes and electrons are combining with each other and we are left with negative and positive ions. So I will try to draw this quickly. I will try to draw the depletion layer quickly. These things are very important because this will help you understand the basics, and after this you can understand any concepts in analog electronics. And if you fail to understand these important points, then it will be very tough for you to understand the coming presentations. First I will make p side. We have acceptor ions on the p side, and on the n side we have donor ions, so we have positive sign for them. Holes are the majority charge carriers in p side, so we have holes as the majority charge carriers, and we have electrons as the minority charge carriers. In the same way, for n side we have electrons as the majority charge carriers, and we have holes as the minority charge carriers. Now the electrons and holes have recombined in this region, so we are left with negative immobile ions and positive immobile ions like this, because holes and electrons have already recombined with each other. And you can clearly see, because of this we have layer of negative charges, negative immobile ions on this side and we have layer of positive immobile ions on this side. So we can say that this is acting as the potential difference. And because of this potential difference, there is an electric field from right to left, that is from positive to negative. There is an electric field like this. Capital E is the electric field from positive to the negative. This is the junction. I forgot to make junction here. This is the junction and this is the depletion region. Now this depletion region is also called as space charge region, space charge region, or depletion layer. Depletion layer, these are the names for depletion region. Now there is one question, why the width of depletion region is fixed? Because this hole can combine with this electron. In the same way, all the holes on the p side can combine with the electrons, all the electrons from the n side, and the width of depletion region is equal to the width of the p-n junction diode. But this does not happen. So what is the reason behind this? As I have already told you, we have electric field developed because of the potential difference, and due to this electric field there is no movement of charge carriers because this positive layer will repel the holes, right? Because hole is equivalent to positive charge and this positive layer will repel the holes, so there is no movement of holes. And in the same way, this negative layer will repel the electrons from the n side. So the width of depletion region is fixed, and as you can see, this potential is acting as the barrier to the movement of holes and electrons. It is acting as barrier for the further movement of free charge carriers. We call it barrier potential. We call it barrier potential, or we call it built-in potential. Built-in potential. Right, and we are calling it barrier potential because it is acting as the barrier for the further movement of free charge carriers. Let's talk about minority charge carriers in this scenario. We are done with the majority charge carriers. We have seen there is diffusion current because of the movement of majority charge carriers, and after the formation of depletion region, the majority charge carriers will not combine with each other and hence there is no movement of majority charge carriers. And as we already know, in case of p-type semiconductor, electrons are the minority charge carriers, and for n-type we have holes as the minority charge carriers. And because of this electric field intensity E, electrons will move to the right and the holes will move to the left. So there is current, and because of drift of electrons towards the positive layer and drift of holes towards the negative layer, we call this current drift current. And this drift current having the direction opposite to the diffusion current. And under steady state condition, the diffusion current is equal to the drift current. Before that, I will complete this. The drift current is due to the minority charge carriers, right? And the diffusion current was because of majority charge carriers. And under steady state diffusion current is equal to the drift current. This is very important point. Diffusion current is equal to the drift current under steady state condition, and we can say that the net current is equal to 0 in case of open circuited p-n junction diode. The net current is equal to 0 for open circuited p-n junction diode. So this is all for this lecture. In the next lecture,
so I think you all of you understand that without biasing, means without supplying the voltage, your p-n junction is act as an open circuit because of this depletion region. So if you want to make this switch on, if you make this diode on, then you must break down this junction or depletion region. So if you applied the sufficient positive voltage, then and then this junction will break down and current will flow from P to N layer. Okay? So this is a basic idea about the construction and operation of the PN junction diode. All of you understand this concept? Is there any doubt to anyone? Yes? Anyone? Is there any doubt? So let's understand its VI characteristic through this second video.
In this lecture, we will study volts ampere characteristics of PN junction diode. X-axis represents voltage across the diode and Y-axis represents current through the diode. In this lecture, we will draw volts ampere characteristics for both forward and reverse bias.
It is the same as the characteristic we have seen the practical, okay, practical of PN junction diode, forward and reverse characteristic. Yeah. But this characteristic you learn in this theory, that is the ideal characteristic. Okay. So if you see that, if you draw the actual practical characteristic, that is somewhat different than this. Yeah. But this is because this is the ideal characteristic of PN junction diode. So let's understand this
Condition, and if you remember the forward bias condition, we connect positive terminal of the battery to the P side and negative terminal of the battery to the N side. So first I will make the circuit. This is the symbol of diode. This is P side, this is N side, and we will connect P side to the positive potential and we will connect N side to the negative potential, and voltage across the diode is equal to VD and current through the diode is equal to ID. Now from diode current relation, ID is equal to IS, where IS is reverse saturation current. In bracket we have E raised to power VD divided by eta VT. This is eta ideality factor minus 1. This is the equation of diode current, and if we consider the condition in which VD is equal to 0, it means voltage across the diode is equal to 0. We can also call it no applied bias. This is the no bias condition, and if you see this plot, you will find this is VD equals to 0 and we have to find the diode current at this point. I will use this equation, ID equals to IS e raised to power 0, because VD is equal to 0. So we have e raised to power 0 minus 1. Now e raised to power 0 is 1. So we have ID equals to IS 1 minus 1. 1 minus 1 is equal to 0. So ID is equal to 0. So this is what we have when the voltage across the diode is equal to 0. The diode current is also equal to 0, and thus we have diode current equal to 0 when VD is equal to 0. Now we will increase VD in positive direction, not in negative direction, and we can say that diode is forward biased, and on increasing VD, width of depletion layer decreases on increasing VD, and also barrier potential decreases, but still diode current is equal to 0 because the barrier potential is strong enough to prevent electrons crossing the junction. But if you go on increasing the VD, if you go on increasing the forward bias potential, VB reduces further, and there is small current through the diode because some electrons will cross the junction and there will be current through the diode. So there is small current through the diode, and when VD is equal to VB, it means the forward bias potential is equal to the barrier potential. There is flood of electrons crossing the junction and we have rapid increase in current, as you can see here. This is the plot of germanium and this is the plot for silicon, and in case of germanium barrier potential is 0.3 volts, and in case of silicon, barrier potential is 0.7 volts. So if we consider the case of germanium, if VD is equal to 0.3 volts, it means VD is equal to barrier potential. There is flood of electrons crossing the junction and current will increase rapidly. And if you increase the VD further, the current will increase exponentially. So there is generous flow of current through the diode if VD is greater than or equal to barrier potential. And in case of silicon, if VD is greater than 0.7 volts or even equal to 0.7 volts, we have generous flow of current through the diode. So this is all for VI characteristics in case of forward bias condition. Now we will move to reverse bias condition, and in case of reverse bias condition, positive terminal of battery is connected to the N side and negative terminal of the battery is connected to the P side. So first I will make the circuit. This is the symbol of diode. We will connect P side to the negative potential and we will connect N side to the positive potential, and the voltage across the diode is VD, and we have to find current through the diode. So we will use this equation, ID is equal to IS in bracket e raised to power VD eta VT minus 1. I will use this, and in this case we have VD negative, or we can say that VD is less than 0. So this is what we have in case of reverse bias condition. This is for reverse bias condition, and if we make VD negative, then let's see what we have. ID equal to IS in bracket we have e raised to power VD eta VT minus 1, and now this VD is negative, so e raised to power VD eta VT is less than 1, and this is when VD is negative. So we can neglect this term and we will have ID equals to IS minus 1, or we can write ID is equal to minus IS. So the direction of current in case of reverse bias condition is opposite to this direction, and we have only one current in case of reverse bias condition, and that is the reverse saturation current, and the direction will be like this. This is IS, reverse saturation current. Reverse saturation current is also called as leakage current. This is also called as leakage current, and this is the only current in case of reverse bias condition. Now we will try to analyze the plot in case of reverse bias condition. This is for forward bias condition, and there is one thing in case of forward bias condition, the diode current ID, it is equal to I majority current due to majority charge carriers minus I saturation, the saturation current. And when depletion layer decreases, when width of depletion layer decreases, the majority current due to majority charge carriers increases, and because of this diode current also increases. And in this case we only have reverse saturation current. In reverse bias condition, we only have one current, that is the reverse saturation current, because I majority is equal to 0. So the diode current is nearly equal to IS because I majority is equal to 0, and we already know the reverse saturation current only depends on the minority charge carriers, and the cause of minority charge carrier is temperature. So the number of minority charge carriers is fixed. Let me write this down. Number of minority charge carriers is fixed, and because of this we have a very small current in the beginning. If we go on increasing the temperature, the current will not change, and this current is IS, reverse saturation current. It is very small current in order of microamperes. You can see in order of microamperes, and this is very small because it only depends on the minority charge carriers, and the number of minority charge carriers is very small. That's why they are called as minority charge carriers, because they are small in numbers as compared to majority charge carriers. And if you go on increasing the voltage, if you go on increasing the reverse bias potential to a higher value, you will find that there is a sudden rise in current. There is sudden rise in current. This graph is for germanium and this graph is for silicon, and there is sudden rise in current. This voltage is known as breakdown voltage. Let me write this down. The voltage here and this voltage here is called as breakdown voltage. Breakdown voltage or Zener voltage. Zener voltage. It is called as breakdown voltage because at this voltage breakdown of diode occurs. Now we have to understand breakdown. What is breakdown? And this is the most important point of this lecture, and it is very interesting and very simple. On increasing reverse bias voltage to a very high value, the electrons will acquire a very high kinetic energy and they will break the covalent bond and become free. These free electrons will again collide with the electrons and free them, and the process will continue like a chain reaction. So what is happening here? When you go on increasing the reverse bias potential, the electrons will gain the kinetic energy. They will have the kinetic energy which is very high, and they will break the covalent bond and collide with other electrons. Now we have 2 electrons. These 2 electrons will go and collide with other 2 electrons. Now we have 4 electrons. These 4 electrons will free 4 more electrons. Now we have 8 electrons. So there is a process like a chain reaction, and we have to be very careful with this condition. So this is the VI characteristics in case of reverse bias condition, and this is VI characteristics for a normal diode, for a simple diode. We also have other type of diodes like Zener diode, in which doping is very high, and Zener diode is very good if you want to operate in reverse bias condition. In Zener diode, breakdown is achieved earlier because it is highly doped. In the coming presentations, we will discuss Zener diode, which is very important topic. We will also solve numerical problems on it. And it is very important to know the voltage at which diode is operated in reverse bias condition, because this will destroy the diode, and we must know the reverse bias operating conditions for a diode. If a normal diode is subjected to the large reverse bias potential, it cannot withstand the high power being dissipated. So we use Zener diode for this purpose. And now there is one term, peak inverse voltage. Let me write this down. Peak inverse voltage, and this is the last point in this lecture. What is peak inverse voltage? It is the maximum reverse bias voltage that can be applied across the diode before entering to the Zener or breakdown region. So this is the maximum value of reverse bias voltage that we can apply across the diode before it enters to the breakdown or Zener region. This is the breakdown or Zener region. Breakdown or Zener region, and the peak inverse voltage is the maximum reverse bias voltage that we can apply across the diode before it enters to the Zener or breakdown region. I will advise you to write this down because sometimes this type of questions comes in exam, and at that point you cannot recall what is PIV or peak inverse voltage.
So I think all of you understand this VI characteristic of diode and reverse bias characteristic. So as we know that generally we use the diode in the forward characteristic. I think all of you understand why we not operate the diode in the reverse region, because as you see that at the reverse breakdown voltage or Zener voltage, your diode will be breakdown because of the huge temperature in the layers. Clear? So that's why we generally prefer to use the diode in the forward region. But we already know that at the Zener diode that we operate in the reverse region because we want to regulate the voltage. Yes, that we will understand in the next lecture in detail. So I think all of you understand this VI characteristic. It is clear, the concept. of diode, PN junction diode? All of you clear the concept?
Yes, sir.
Okay. So now let's understand what is the application of this diode in the electronic circuit. So as we already discussed in the last practical, half wave and full wave rectifier. Clear? So what is the application of half wave and full wave rectifier? So we already discussed that we use as a power supply, DC power supply, like mobile charger. Clear? So this is one of the application in which you can use the diode, half wave or full wave rectifier. Clear? So in the next lecture, we will discuss the detail about the half wave and full wave rectifier operation. Clear? We already understand the operation in last lecture, but we again discuss this in detail. How it is operated in half wave rectifier and what is the function of this diode in this rectification process. Clear? So as you already discussed that there are two types of rectifier. One is half wave and full wave rectifier. Clear? These are the another application of this diode like clipper circuit, clamper circuit, voltage regulator circuit like Zener diode. Clear? But in this chapter we understand only these two application or these two circuit, half wave and full wave rectifier circuit. Clear? So we already understand this kind of block diagram of power supply. We require the AC supply, apply to the transformer which step down the voltage. Then step down voltage apply to rectifier. Rectifier convert AC to DC. Then your DC is not a pure DC. It contains a ripple, harmonics. So to remove this harmonics from the output voltage of this rectifier, you use the filter to filter out the harmonics. And after the output of this filter, you get the pure DC. But again, if you require the regulation of this voltage, then if you apply this output of filter to the regulator circuit. Yeah? And then after you get the regulated DC output voltage. Yeah? And then you apply this regulated output voltage to the any node, like a mobile charger. Yeah? So this is a single line diagram of power supply by using the rectifier. So in the next lecture, we discuss detail about the operation of this half wave and full wave rectifier. Okay? So here I stop this lecture, and next lecture we start this. Tomorrow we start with this topic of half wave and full wave rectifier. Is there any doubt to anyone?
Sir, please share PPT of 7th chapter.
Okay, I will share it. Okay. Okay, so you can leave this meeting.